Hello, I'm René Grotman, the author of Euler Math Toolbox, and I'd like to start a series of videos about the program. The first aspect I'm going to talk about are floating point numbers. Euler internally handles floating point numbers. On the numerical side of Euler, floating point numbers is the basic ingredient of all computations. So let's enter 1 over 3 into this command line and press return. We get an output of 12 digits. This is not the complete internal representation of the result. You get the complete result by saying longest 1/3. The operator longest now prints 1/3 in 16 to 17 digits. Of course, that's not the internal representation of 1/3. The internal representation of a floating point number is dual. We get that by saying print dual 1/3. Now we have about 54 dual digits of the number, reading 1.01, etc. times 2 to the power minus 2, which is 1/4. So we have 1.01, etc. times 1/4, which exactly is 1/3. If we continue the digits eternally, but as you see, we have to stop at some point, which makes an error. The error is called the internal epsilon for the floating point operation. The answers of Euler are somewhat deceiving. For instance, if you print pi, you get 12 digits of pi. If you take the sign of that number, you get 0, which seems to be correct, but in fact Euler is not computing the double arithmetic of Euler, is not computing sine pi exactly. It is not exactly 0, in fact. Let's check that with another format. To set the format permanently, we use longest format. Now we get more digits of pi, and we don't get 0 exactly. The longest format also turns off the rounding to 0 of small results. That may be confusing, but it is the fact of life. This pi is correct to 54 dual digits, and the last digit is wrong. Large digits is wrong, of course, it is off. So sine of that is not 0. Another example of this fact is 0.1 added 10 times 8, 9, 10, which is not exactly 1. If we subtract 1, we get an error. It's about the same magnitude as the error of sine pi. Note that the double error is relative to the number. For example, let's take x minus 20. That's a small number, but all 16 digits of this number are correct. To prove that, we multiply the number that we just got by x 20. Mathematically, this should be 1, and in fact it is. This is by chance rounded to the correct value 1. Not all results are rounded to the correct value. 1 over 3 times 3 is, but 1 over 49 times 49 is not. So how do we check for 1 if we want to check for 1? We cannot compare to 1 because that will yield 0, which is false in Euler. Euler has the operator about is about equal, like this, and that will yield true. It compares the two numbers with respect to the internal epsilon. That's several magnitudes larger than the double epsilon to make sure that we catch all results. Often people ask about computations with more digits in Euler. That's possible via Maxima. Maxima is accessible by symbolic expressions. So if we enter ampersand, we get a symbolic expression, and let's talk about x minus 20. If we enter that, we get a symbolic result. But we convert that into a floating point number in Maxima, not in Euler, in Maxima, by adding float. That's the same result we had previously. But we can also enter big float, and we get a lot more digits. Other ways of doing this is starting with floating point numbers. For instance, if we say 1 over 3 times 10 to the power 0, which is nothing but 3, we get this number, which is 1/3 to 32 digits. Or we can say 1 over 3 and with a modifier big float, which gives the same result. The accuracy of the floating point numbers, of the big floating point numbers in Maxima, is controlled by a variable called floating point precision. We can set this variable to some other value, say 100, and then we can print the result. Sorry, to 100 digits. Euler does not have integer arithmetic, but integers are representable in dual format up to 16 digits. Let's try that. That's a correct result. Compare with the symbolic result, with just the same. Let's add some more multiplications, and we exceed 16 digits, and we get only 16 correct digits out of 19. The same in symbolic form yields all digits, of course. Note that symbolic computations are very much more slow, orders of magnitude slower. So you should use them only if you need to. So much about floating point arithmetic and floating point arithmetic with big floats and normal floats in Maxima and symbolic expressions, and about integers in Euler Math Toolbox. Have fun!